All right, in this podcast, we're going to talk about the relationship between Gibbs free energy and our cell potential for a galvanic cell. All right, so we've already talked previously in the year about thermodynamically favored reactions. Those are ones who have a negative delta G. Redox reactions, if we know what their E cell value is, their standard E cell value, then we can determine if the reaction is thermodynamically favored or not. So basically, it will give us a sign for delta G. So if our E cell value is greater than 0, that means it is a thermodynamically favored reaction. It should happen. And if it's less than 0, so negative, then it's not going to be thermodynamically favored, not spontaneous, not favored. All right, so looking at this reaction, we are to try to determine if this is a thermodynamically favored process or not. So first thing you need to do is you need to take out your spectator ions. So we got Ba2 plus and the Pb solid. And that's making the Ba solid and the Pb2 plus. Okay, so now we need to get our half reaction set up. So Ba 2 plus is definitely in the reactants, so that's going to be this guy right here. So that means we do not need to flip the value. So we got negative 2.90. And then we have lead solid in the reactants. Up here it's in the product, so we flip it. So 0.13, and we add those together, and we get negative 2.77 volts. Since it's a negative delta E, that means this is not favored. All right, this is an equation that helps us quantitatively understand the relationship between Gibbs free energy value and the standard E cell for electric potential for the cell. It's given by this formula right here. Delta G equals negative N F times our E at standard values. So N is for the moles of electrons in the balanced redox equation. F is a constant called Faraday's constant. It is 96,485 coulombs per mole of electrons. And then, of course, our E cell value is going to be in volts. All right. So in general, the more negative delta G becomes, the more spontaneous the reaction, the more favored it is. So the higher our E cell should get. And the more positive delta G becomes, then the more negative our E cell gets, because this is a non-thermodynamically favored process. Okay, so we are asked to solve for delta G, okay, and notice that we have zinc in our reactants, and it's in the products in this equation. So that's going to flip the sign of that voltage. And then our copper 2 plus is in the reactants on both sides, so we're just going to keep it the same. So we add those together, and we get an E cell value of 1.10 volts. Now, if I plug this into my equation, okay, the number of moles of electrons. Well, you'll notice in the half cells reactions, the number of electrons are the same, and they're 2. So it's definitely going to be 2. And then Faraday is our constant. And then our E cell value was 1.10. All right, and we multiply all that out, and it gives us a delta G of negative 85,000. There we go. Negative 85,000. All right, now in this one, we have a little bit more complex reaction. We're asked again to find delta G. Okay, so Mn is right here, and as you notice, it is flipped, so I'm going to flip my value, so 1.18, and then my chromium is the 3 plus in my reactants, and that's exactly how it appears here. So 1.18 minus 0.74, and we get 0.44 volts. That's our E cell. So if we're going to plug this in our delta G equation, next thing I need to find is my number of moles. Okay, so if you'll notice up here, our reactions give us 3 and 2. We know the only way they're going to get to be the same number is they're going to have to get to 6 electrons. So -6, and then my Faraday's constant, and my E cell value I just calculated, and I get my delta G is equal to negative 255,000 joules. All right, next it wants us to estimate the equilibrium constant Kc. All right, since this is a pretty large negative number, that means that my K is going to be a very large positive number. So, big positive number.